Okay, so let us begin by first revising what we covered in the first lecture very briefly. So in the first lecture, what we looked at is that initially we started out by looking at classical robotics. Can all of you type some of the drawbacks of classical robotics which you remember from the last lecture in the chat? Okay, Yashwant says under modeling issue, Uday says complex maths. Tanmay says cannot reach the desired location due to parameters like friction. That is very similar to under modeling. So first one you guys have already covered, which is under modeling. Okay, what are some of the other issues? Safety hazard, which Ajiket is saying, it's not a issue related to classical robotics particularly. It was an issue with respect to reinforcement learning, where initially the robot starts with random actions, which happens in the exploration phase. And that's why it can be a safety hazard, which is solved with the technique of imitation learning.
Okay.
We will revise that in a while. Paresh point is correct, cannot scale with data. So these 2 points we can easily understand. There are two more drawbacks. Can anyone remember those drawbacks? Those are not very straightforward. You don't see it directly on the surface, but they are still very important to consider. So this is the first one. This is the second one. The third drawback is known as multi-modality issue. This we had discussed in the last lecture. So
Multi-modality.
multi-modality means that let's say you have a robot which you are training on some data. Now, if that data is comprised of not only information about the joints, but also the input which is coming in from the camera feeds. Then you have text-based data or numbers, plus you have information coming in from the cameras. So you have multiple modes, or you have a text mode, you have an image mode, and you need something which can combine these both these modes together before it is passed as an input to your model. So this is something which classical robotics cannot handle. And the way which uh, implicit methods or learning based methods can handle this is that they can extract features from the input. And feature extraction is mode agnostic, which means that you can extract features from text based data, or you can extract features from image based data, or even video based data for that matter. So this is one of the key drawbacks. And the fourth one, which Sri Harsha has already mentioned, is the brittleness in the pipeline. So this typically happens because in classical robotics, you have different layers. It's like stacked on top of each other. You have a perception layer, then you have a control layer, and there are two more layers. So it's a pipeline which is very brittle. Even if one of these layers fail to perform, your entire input output stream gets affected. And this is something which is solved through implicit models, because implicit models, you simply have a model, or it is also called as policy, and you give a set of observations to this policy and you get out a series of actions from the policy. So you're not having these multi-stage pipelines within the model or the policy, which is what makes it more robust compared to classical robotics. Okay, so classical robotics typically includes forward kinematics and inverse kinematics as well. Uh, and then it's something which is people used to use a lot for 50, 60 years. However, it's not very practical. But still, it's important for us to understand the meaning of forward and inverse kinematics and where the literature had progressed until we stumbled upon RL and imitation learning. Now, after this, what we looked at was reinforcement learning. Can you guys list down in the chat what are some of the drawbacks of RL? One of the drawback Ajiket has already mentioned is the safety hazard. What else? Sparse reward. Yes, this is also valid. What else? Poor generalization is something which happens in both the cases. It happens in RL, it happens in IL also, which is imitation learning. Yeah, so resetting the environment is another drawback in RL. It's not straightforward to reset the environment. But the first two usually dominate the list of drawbacks. And because of these issues, RL is still popular, but it's not the only method which you need for all possible use cases. After you have after reinforcement learning, another parallel stream emerged, which is called as imitation learning. Now, in imitation learning, we learned something very important. In imitation learning, what happens is you have a robot model, which is also called as policy. The policy takes in observations and predicts actions. Can anyone tell me the size of these observations and actions for the SO101 arm? How many dimensions is the input vector and how many dimensions is the output vector? So great. All of you are getting this correct. You have six-dimensional inputs and six-dimensional outputs. And the observations consists of not just the proprioceptive data. Proprioceptive means the information about the robot's own joints, which are the 6 degrees of freedom, the 6 angles of the robot. You also have the visual data. And this is the observation you have for every single time step. So let's say you are recording with a 30 frames per second. So each frame becomes a time step. So within 1 second, you have 30 time steps. And for each of these time steps, you are collecting a bunch of observations and you are predicting the actions. Now, actions are the 6 joints, the positions of the 6 joints of the robot. So you can see there is some mismatch between the dimensions of the observations and actions, but that doesn't matter to us because we are anyways training a machine learning model to map the observations to the actions. Okay, so now this is the main technique of imitation learning, and it solves these issues because you don't start randomly, but you ask humans to record a bunch of trajectories, and humans are not going to start with some random actions. These are expert humans. So we took the example of pouring milk in a coffee. So you are going to start with proper demonstrations, and the reward is implicit within the demonstration itself. So if I'm drawing a shape of a heart on the coffee, I'm telling the model that this is the shape which I want. So implicitly, I am favoring trajectories which are drawing that shape. I am not explicitly saying that the reward is +1, 0, or -1. So this is imitation learning. Now comes the main point of the last lecture, which is going to lead up to this lecture, which is the drawback of imitation learning. Does anyone remember the drawback of imitation learning? Or I think I should frame it in a different way. What is the drawback of point estimate policies in imitation learning? Remember, point estimation policy is a function which takes you from observation to actions, where for each observation you get one single action. Does anyone recall? So, yeah, so what usually happens is that point estimate policies are not good enough for data that is multimodal, which has multiple modes. So, for example, if you have a robot here, and let's say this is the arm, and there is an obstacle over here, and there is an object which the arm is supposed to pick up. So you can either go from the right to pick the arm, or you can go from the left side to pick the arm. So there are two modes. There is mode 1 and there is mode 2. But point estimate policy is only going to favor one single action for each observation. So it doesn't really understand that there are two possible ways of completing the task. And this failure is inherent in the way we have designed the policy itself. We have told the policy that given a bunch of observations, given the proprioceptive data of the arm, this is the action that you are supposed to take. But we are not telling it that, okay, given the observation, these are the possible actions that are available at your disposal. So this is the major drawback, and this is what is going to lead us to this field of generative modeling. So we are going to cover this in detail in today's lecture. And I think this will also help you understand this problem much better. Maybe some of you are not able to visualize this very cleanly. What do I mean by point estimate policies, and how do they differ from policies which are probabilistic in nature? So we will look at some practical examples to help you understand that. Okay, so just to help you think more before we start the lecture, I came across a very interesting practical demonstration of the SO101 robot today. So what these guys did was they asked like a text query which was fed as an audio input. So let's say the text query is draw the picture of the house. Then this text query was fed into an LLM. Uh, and then this LLM, it gave the coordinates of the house. Now they had two different robots. There was one robot which actually drew this trajectory. And then there was another robot which was trained through imitation learning to clean this trajectory. So what do I mean by clean? This trajectory is drawn using a marker on a whiteboard. And the robot number 2 takes a sponge and cleans the trajectory, which is drawn on the whiteboard. Now, the reason I am showing you this example is that this is one perfect example where you see both classical robotics explicit models and implicit models working together in tandem. So this robot 1 This was an explicit model where they used inverse kinematics to predict, given this location of, so I know how my end effector should move, right, to draw this shape. So given the position of my end effector at all time steps, how do I control the proprioceptive data? How do my six joints change with each time step? So this was drawn by the first robot, but the second robot was trained using imitation learning. So they recorded around 100 different trajectories of a robot taking a sponge and cleaning uh, the trajectory which was drawn by robot 1. So during testing, what happens is that, let's say I give a text query which is draw a circle. The LLM goes ahead and draws a circle, or the LLM predicts the coordinates of the circle. Robot 1 uses inverse kinematics to understand how should the joint angles move to draw this circle. Then robot 2 comes into the picture. Robot 2 is already trained using imitation learning. It is trained using a probabilistic model. We don't use a point estimate model over here. But then it is already trained, so it looks at the data. It understands that, okay, this is where the marker is there on the whiteboard. And my job is to take the sponge, put it on the marker and move it in such a way that finally the ink disappears. So this is, I'll share the video with all of you, but I wanted to share this today before we start the class because I think it conveys these concepts of explicit and implicit models very nicely in one single example. Okay, so let's start today's lecture now. Today the main focus is going to be on deep generative modeling. And I understand that some people find it very hard to think in terms of probabilities. For us, what comes naturally is that given an input, this is the output. But very few of us are actually comfortable to think in terms of probability distributions. So I'm trying to make this lecture more intuitive so that all of you should get comfortable with distributions. And what does it mean to predict a distribution? What does it mean to sample from a distribution? So let's understand that in detail. So first we'll take a simple example. Imagine that you have the heights of 1,000 students in your school, and you only have the samples of the heights. You do not know the true distribution of all the possible student heights. So it can be any distribution, but you have no idea what the true distribution is. All you have is you have individual samples which are collected from a few students. You don't have it from all the students. Maybe you have 100 samples, 120 samples, etc. Now let us say that a new student joins your school tomorrow and someone asks you the question that, can you generate a realistic height for this student? Can you predict what the height of this student could be? Okay, so once this problem is given to you and you do not have the true distribution, then how are you going to solve this problem? Let's try to understand this. The height of the new student will depend on the probability distribution of the sample data. For example, if you have collected the students' heights for students who are less than 10 years old, your samples will be of less heights. But if you have collected data for students who are more than 15 years old, your sample will have higher heights. So first, let us look at the true distribution. Okay.
Mhm.
So let's say the blue distribution is the true distribution. And this is the distribution that you want because you can then sample from this distribution and predict the height of the new student. But the problem is that this blue distribution is not available to us. All we have with us are these heights. So you can see this yellow distribution which appears in the background. It is the samples which we have collected. And it is somewhat following the trajectory of the blue distribution, but not quite. And if you collect very less samples, then the distribution will be even more further away from the true distribution. Now, this is exactly what a deep generative model will try to learn. The objective, which will again keep on repeating in this lecture, is the objective for us is to develop a model which can predict a probability distribution. So far, probably in your machine learning courses or some of the classes that you might have taken, all the possible examples that you have seen, let's say supervised learning, unsupervised learning, every single example predicts an output given an input. You don't predict a probability distribution. Now we are going to see an example where we are going to build a model that not just helps us to predict one single output given an input, but we predict the entire probability distribution. So for example, our model will try to predict the true heights like this, which is shown in green. And if our model does a bad job, initially maybe our model is over here, which is very far from the true distribution, right? But then let's say you sample from this, you might concur that, oh, the height of the new student is maybe 140 centimeter. But that is wrong, right? You probably would most likely sample from this one, which has the highest probability density, which is around probably 165. But because your prediction was so far off from the true distribution, your sample from this predicted distribution was very far off from the sample that you would have predicted if you would have access to the true distribution. Okay, now we'll look at some notation which will be consistent with. So this is the true distribution, which is known as p data of x. And our predicted distribution, we are going to denote as p phi of x. So deep generative models are trained so that the predicted distribution matches as closely as possible to the true distribution. So let's look at a visual representation. I have made some videos here using Manim because I think this lecture will be more effective if we can visualize what we are talking about. Let's try to understand this. Okay, so on the x-axis you have the height and on the y-axis you have the density. This is the same example which I discussed. So the blue is the true distribution which we want to predict. And initially our model starts off somewhere on the left, which is a very badly trained model. Maybe it's the initial starting point. And what we want to do is slowly morph this distribution so that it roughly is centered around the true distribution. And whenever we are training a deep generative modeling or a deep generative model, under the hood, this is what is actually happening. It is trying to change its curve so that it matches the curve for the true distribution as close as possible. Ajiket, please mute yourself. We can hear from your audio. Okay, so let's try to formally understand what is deep generative modeling. Okay, so similar to the example of students' heights, which we looked at, deep generative models take as an input a large collection of real world examples, which are drawn from unknown and complex distribution, and they output a trained neural network that parameterizes an approximate distribution. So in this example, we looked at the heights of the students, but in practical use cases, we will have examples which probably include images. Let's say the true distribution is the images of cats. Now, this is something which humans cannot even imagine. Uh, we cannot draw a probability distribution for cats, right? We can probably draw a probability distribution for students' heights, but how does a distribution which can represent all possible cats in the world look like? So the fact that even scientists thought of modeling images as representations is very astonishing to me because it's not intuitive at all. That you can create a probability distribution for specific categories like cats, dogs, or anything you can imagine. But it is possible to do that. And in fact, a lot of these image generation tools which initially came out, like Midjourney, Stable Diffusion, all of them were deep generative models. So we have cracked this, but we are going to look at the exactly how this was possible. So there are two main goals of deep generative modeling. Firstly, the generation should be realistic and it should be controllable. Okay, so now some assumptions before we move ahead. We assume that the samples are drawn independently and identically distributed from an underlying complex data distribution. And in fact, this is something which is a requirement even for supervised learning. Let's try to understand this a bit more better. If you look at robot training data, then let's say we collect our observations at time t, which is a bunch of proprioceptive and visual data. And then you collect the observation at time step t plus 1. Now, my question to all of you is that are these samples independent from each other? What does your intuition tell you? Do you think the samples are independent or dependent on each other? So many of you are saying that they are dependent on each other, and in fact, that's true. What you see at time t plus 1 is heavily dependent on what you see at time t, and which means that they are not independent of each other. So the way this problem is solved in the field of robotics is that you create a bunch of trajectories. Let's say you create 5 trajectories, and in each trajectory you collect 100 time steps. So what you do is you shuffle and mix the data. So you don't show the model sequential data, but you randomly pick 10 samples from this and then train on that. Then you again pick 10 samples, again train on that. So this is very similar to the concept of replay buffer, which exists in deep reinforcement learning. And I just want you to keep this in mind before we go ahead so that you understand the meaning of this first line. Okay, so the primary goal of DGM is to learn a probability distribution from a finite data set. And DGM uses a deep neural network to parameterize a model distribution where phi represents the network's trainable parameters. This we have already looked at before. Essentially, what we are going to do is we are going to match P data of X with P phi of X. That is going to be our strategy. Okay, so let's try to understand how do you even define the loss function for this, right? Because in supervised machine learning, let's say uh, Y data is your true predictions and Y star is the data which your model predicts. So you can write down a mean square error loss, which looks as like this. And then you can sum it up for all data points. So this makes sense. But if you have two probabilities, where one is the true probability distribution and one is the predicted distribution, then can you simply do something like this? Something looks odd about this, right? So we'll understand how the loss for the probabilities are actually calculated. Okay, so now what we'll do is we will extend our example of students' heights to a slightly more complex example where we are considering cats. So now let us say that we are given a bunch of cat images as follows. Okay, now the task is we want to create or learn a probability distribution that matches this true probability distribution as much as possible. The biggest problem with this kind of a formulation is you do not know P data. You knew Y data in the supervised learning example, but what is the probability of, let's say, sampling this cat from all the entire distribution? We don't know. All we have is we have access to the samples. We have individual cat images, but we do not know the exact probability distribution from which these images are drawn. So this we do not have access to. So now if we have understood the goal of DGM correctly, our next step is to find a probability distribution which matches the true distribution of the data. So let's imagine hypothetically that this is the true distribution of P data. So what we want to do is we want to find a distribution that matches this distribution as close as possible. So at least the first objective which comes to my mind is the KL divergence. Has anyone of you heard about KL divergence? Just mention in the chat if you have or have not. Okay, so let's first understand. Okay, some of you have not, some of you have heard of KL divergence before. So we are going to look at what is KL divergence also in a while. What is the purpose of all of this? You might wonder, right? Why do we want to predict this P phi? The purpose of predicting probability is that later, once you have the probability, you can sample from it and generate new samples. This is exactly how applications like Stable Diffusion or Mid-Journey work. Let's say I type create an image of a cat. What happens is that this request goes to a deep generative model, which probably has a complex probability distribution for cats. And then all you do is you pick a sample from that probability distribution and then you generate an image. So the reason why these models are so valuable is that once you have the probability, you can sample from them. And now you can link it back to the issue of point estimate policies, which we had for imitation learning. If we learn the probability distribution for all possible actions for every observation, then we can simply sample from that and we can get observations which can possibly capture multiple modes. We are not restricting ourselves to one single action. So just let's say try to visually understand this. Let's say you have two actions of +1 and -1. And for a particular observation, if my probability P phi looks something like this, I can clearly see that there are two modes, right? I can either go here, I can take an action of -1 or +1, but I will most likely maybe 8 out of 10 times take +1 because the probability is high. But at the same time, I am not restricting myself that I'm only taking an action of +1. There is a chance that I might take the action of -1 also, but the only difference is that the probability of that is less compared to taking an action of +1. This is exactly what we were looking for to uh, circumvent the issue of the point estimate policies. Now let's try to understand the meaning of KL divergence. So KL divergence is one parameter, or we can say it's like something which quantifies how two probability distributions differ from each other. So if you have two distributions which are very distinct, the KL divergence is very high. If you have two distributions which are very look very similar to each other, the KL divergence is less. So let's try to visually understand the meaning of KL divergence. Okay, so what we have done here is that we have considered two distributions. The blue distribution is the true distribution, which is denoted by P of X, and the model distribution is in orange, which is denoted by Q of X. So here we have three different observations, and we have probabilities for all these three observations, A, B, C. Okay, so let's see. Now, for A, you can see that the true probability is 0.5, but our model has predicted 0.2. So if you simply take the difference between the two, you get 0.3. Okay, so absolute difference is something we can start off with, but it's not something that people use in practice. So this is something which does not capture everything. And we will understand why it does not capture, but let's look at the alternative for to capturing the absolute difference, which is to take the ratio. So if we take the ratio P of A divided by Q of A, if the ratio is very large, it means that our model is uh, thinking that the observation A is not very likely, whereas in reality it is very much likely. So the ratio is indicative of something, right? A very large ratio means something specific. Whereas if you take the difference, you won't get values which are very large ever. You'll just end up with values between 0 and 1. So ratio helps us to understand whether our model is overestimating the observation or underestimating the observation. So here it's underestimating in this case. Now, in the third case, you can see that our model overestimates because the ratio is less than 1. So whether the ratio is greater than 1 or the ratio is less than 1, you are getting different interpretations. Now, let's go ahead and understand this even more. Now, something which captures this is the logarithm of any function. So let me just, before we go ahead, this is the plot of log of x. This is x equal to 1. So now what we saw from this is for ratios which are in this range, very high, this is underestimation. And this is overestimation. So why log is used is because logarithm converts these values into positive and negative. So now we can clearly say that whatever numbers are uh, underestimating your observation, the logarithmic term is positive for them, and which is in this region. And whichever uh, terms have a negative or less than 1 log value, it is overestimating because here it lies in the negative zone. So that is why people use logarithms. Let's try to go further. So this is the first half of the story for KL divergence, where logarithm is used to understand how the two models differ from each other. When the logarithm value is positive, it means that our model is underestimating the true value or true observation. And if the logarithm is negative, it means that our model is overestimating the true value. So now you might think that is log of P of x divided by Q of x the formula for KL divergence. We are very close, but we just multiply it by P of x at the end, which weighs how important the outcome is. So if you look at observation A, you can see that P of x is very high, right? Which means that if our model is either overestimating or underestimating whatever it is doing, the penalty for doing that should be very high compared to observations B and C. So that is captured in this P of x. So the final formula is P of x into log of P of x divided by Q of x. And the notation is this DKL P given Q. Most of the people that I have met, they do not understand this intuition. All people remember is that KL divergence is something which captures how the two distributions are close or different from each other. But if you actually dig down, this is what the formula actually comes from. This is where it comes from. So when Q is very close to P, the KL divergence is zero. Why it is close to zero? Because the ratio is 1 and logarithm of 1 is 0. That's why this term becomes 0 when both the distributions are very close to each other. Now, you will see that in a lot of papers in robotics or deep generative modeling, this notation is used, which is DKL P given Q. And I don't want you to get intimidated from this notation. It simply means that how close or away are these two probability distributions from each other. And the formula for this is P of x into log of P of x divided by Q of x. Okay, so the final number tells us how far the model distribution is from the original distribution. So we are going to use the KL divergence at some point, but right now let's just keep it at the back of our mind before we move ahead. Now, some of the main challenges in modeling distributions is that you have to ensure two main things. The first thing is that the probability should be greater than zero for all the values, and the integral over the entire domain must be equal to 1. So this is something which I will not go in too much detail right now, but usually what people do is that they use an exponential function to ensure non-negativity, and enforcing normalization is not very simple, but we will understand this using this video. Let's see. Okay, so what happens is like if you have, let's take an example of three people having three marks, 40, 30, and 20. So the total score is 90. And if you turn these into probabilities, you can see that 40 divided by 90, etc., they are adding up to 1. So what people do is to convert scores into probabilities. Let's say we started out with the values of 1,000 students in the class, right? So if you turn these values into some scores, let's say we just consider three students A, B, C, and you take scores for them, which is 20, 30, and 40. Now, if you add up these values, it adds up to 90, which is not what we want because it does not satisfy this second rule. So usually what people do is you divide these values by the sum. So A becomes 20 by 90, B becomes 30 by 90, and C becomes 40 by 90, so that all of this adds up to 1. So whenever you see any deep generative model, people have constructed the model in such a way that, first of all the outcomes should be non-negative, and the integral over the entire domain should add up to 1. Okay, now we come to a very interesting part, which are the different types of deep generative models. And in this bootcamp, we are going to cover only one of these types. But I want you to be aware of the entire spectrum which exists in the literature so that you can also explore some of these models on in your own time. The first set of models are called as energy-based models. Now, energy-based models are very interesting because what they do is they work on a very simple concept. Energy-based model says that assign lower energy to data points which are more probable and assign higher energy to data points which are less probable. So this is very similar to, let's say, this is a valley and you drop a tennis ball from the top of this valley. Where is this tennis ball most likely to land? It's most likely to land at these points, point number one and point number two. Why is it most likely to land at these points? Because these are the points which are called energy minimas. So whichever points have the lowest energy, the likelihood of the ball falling in those points increases. A similar analogy is used in these energy-based models. So here, if you look at the energy for the different scores which the students have obtained, you can see that for the score 80, the energy is the minimum. And that's why the probability for this point has to be the maximum. So this is the probability curve. So 80 corresponds to a very high probability. That's the only logic which energy-based models use. So we will again understand this visually through this visual animation. So what we have is we have exam scores which we have collected from students, and for each of these exam scores, we have calculated an energy function. And we can see that the energy function attains its minima for an exam score of 70. And this is exactly the point where we want our probability to be maximum. So in the later curves, you will see the probability curve being plotted, and the probability looks in such a way that this point has the maximum probability, which is exactly what we want. Okay, so this is a brief intro about energy-based models. The second are called as autoregressive models. All of us know autoregressive models because we have learnt about LLMs in the past. How many of you know the meaning of autoregression? Can you just type in the chat if you have heard about this word before? Okay, I think all of you have heard about autoregression, so I'll not spend time in explaining about it. Autoregression simply means that we are predicting the next token. So we are generating outputs one piece at a time, and the next piece depends on everything that has been generated so far. Then the third important type, which is the variational autoencoder, and this is exactly what we are going to focus on in today's lecture. So this is something which is very important, and the action chunking with transformers, which is the policy which we are going to train on the SO101 ARM, uses a variational autoencoder. So we will understand this in complete detail. And finally, we have normalizing flows, which is the fourth technique which people use in deep generative models. So I just expect you to be familiar with these names. I don't want you to understand all these nitty-gritties of all these deep generative models in detail. We will go into depth to understand variational autoencoders now in the next part of this lecture. Okay, so we will start with a very simple question which we'll keep on repeating for the rest of this class. The question that we'll start off with is that imagine you have collected handwriting samples from the students in your class. Imagine that there are 100 students in your class and all of them have written the word hello. Okay, so all of us can write hello in different ways, right? Let's say some of us write it like this. Some of us, some of us write it like this. So there are many different variations in which we can capture it. So students will write hello in very different ways. Some of them will be slanted left, some of them will be slanted right. Some words will be neat, some words will be messy, etc. Now, if someone comes up to you and asks you a question, create a machine for me which can produce samples of handwriting for the word hello written by students of your class. How will you do that? Now, this question itself is somewhat challenging because first of all, there is so much variation in the writing style of the students that how can we design a machine which can first of all capture this variation and then generate an output which can produce a sample which appears like a sample which has come from this class, not from any random class in the world. So how will you solve this problem? So the first thing which comes to your mind is there are many hidden factors which determine the handwriting style. So for example, let's say, I think someone has, okay, yeah, Pramod says capture probability distributions. Yeah, but the thing is, how will you capture the probability distribution? How will you capture the distribution even? Let's forget about probability. How will you capture this variation which is there in the handwriting samples? So the first thing coming to your mind is what are the hidden factors which determine the handwriting style? And there are many factors. There are the every handwriting, let's say, depends on how much pressure the students apply, whether they write slanted, whether their letters are wide or narrow, how fast they are, etc. But something makes me think that if we capture these hidden characteristics, we can maybe produce some realistic samples coming from this particular class. So okay, fine. So let's try to understand this better. These hidden factors are not directly seen in the final image, but they are definitely causing the shape of these letters. So what you can think of these hidden factors are that every single handwriting sample has some specific combination of these hidden factors with some specific values. Like let's say someone applies a pressure of 3 pascals, someone writes left, someone writes wide. So speed is, let's say, fast and messy. Then you pinpoint it to handwriting of Rohan in the class. So once you have the values for all these hidden factors, you can pinpoint it to one specific handwriting style coming out from your class. So these hidden factors, which we'll also call as a secret recipe, which determines the handwriting style. For example, the person writes slightly tilted, thin strokes, medium speed, moderate neatness, etc. So, okay, if once we look at this, we can probably think of the general architecture of the machine, which looks like this. We have the secret recipe, which is given as an input to the machine, and the input generates hello. Uh, Now, okay, fine. So this at least this now we have some structure to this machine. We are not starting from random. We are thinking of if we know a secret recipe, if we know the hidden factors. So these are also the hidden factors. If we know the tilt, if we know the neatness, if we know the pressure, if we know all of this, we can type in the machine and then so imagine the machine has, let's say, 5 knobs. Knob 1, knob 2, knob 3, knob 4, and knob 5. And we can basically control all these knobs. And once you control, let's say you press a button, which is like a print, and then you get the handwriting, which is this handwriting. Now, this is something which we are thinking in this direction. But the main question is that how do you find these hidden factors? So let's try to think about it. But in a more formal term, these hidden factors are also called as latent variables. So whenever I used to read research papers, I used to see these words coming, this phrase coming very often, or this term called latent variable. And it seems somewhat intimidating, but all it means is we are capturing the hidden factors which are causing the variation in the images. So they are called latent because they are hidden. They don't present themselves to you directly when you see the handwriting, but you have to dig a level deeper to understand what these latent variables are. So this concept of digging a level deeper to first go to the latent variables and then generate the image, that is the intuition that I want all of you to understand. That it did not come very naturally to us, right? That we want to identify these latent variables or these hidden factors first. But this thought process that let's not go with the image generation directly, but first let us understand the hidden factors of variation, because once we understand that, we can probably generate different type of samples which are coming from that same class. So these variables are also denoted by the symbol Z, and they capture the essence of how the handwriting was formed. Okay, so let us assume that for the rest of this lecture, we are going to assume that we have only two latent variables, one which captures the slantness, which is denoted as Z1, and one which captures the neatness, which is denoted as Z2. So these are the latent variables that we have chosen to work with, which is Z1 and Z2. Okay, so now can can you guys think how do we obtain this Z1 and Z2 from our image? How do we go from the real space to the latent space? Preetham says that is the latent variable related to pixels. Okay, and anyone has an answer for this question is how do we go from the real space to the latent space? Shriya says that encoding. Paresh also says encoding. So it's the correct answer. The formal word for this is called as an encoder. So we need to somehow encode our handwriting samples, which are the images, into a latent representation. Now, what does the latent representation looks like? Let's have a look at that. Ajiket says define a structure for the latent space and compare the real space with it. Yeah, that is also very interesting. But first, let us look at only the first part, which is the latent space. So we want to convert the real samples from the real space to the latent space. So the latent space looks something as follows. You have on the x-axis, you have slantness, and on the y-axis, you have neatness. My objective is to transform every single handwriting sample that I am given into these latent space. This itself is very astonishing, I think, because, okay, in reality, you might have maybe 64 to 128, any number of latent dimensions. But let's work with two dimensions for now, Z1 and Z2. But the, uh, what do we say? This transformation of every single letter into another dimension, which can represent everything about that image, that is astonishing. So what we are trying to do here is every single image, let's say hello, it is divided into 28 by 28 pixels, right? So there are possibly 784 values for each image. So from 784 dimensions, we are converting it to two dimensions. So it's like a zip file which we have on our PC, something which compresses the information so much, but you don't want to lose the information after you compress it. You want to keep the information intact. And this is what is happening in this latent space. We find these variables Z1 and Z2, which are slantness and neatness. And you can see that as I go on the right, they are slanted towards the right. And as I go on the left, they are slanted towards the left. And on the top and the bottom, I have handwriting which is not very neat. But in the center here, this is where the neat handwriting lies. If you go slightly to the top or the bottom, you will get handwriting which is probably it's not very neat. You can't even make out what's written. And every single student, let's say the student Rohan, which we said, every student can be mapped to one specific point in this latent space. So for example, this is Rohan. So this is one student, then this is another student, this is another student. Like this, you create a mapping for 1,000 students, which probably looks something like this. All the students in your class can be mapped into this latent space of handwriting styles with 2 dimensions. So this is the first step in our machine where we transform the samples, which are the image samples, from the real space into the latent space. Okay, so now we feed this into a machine and then we generate the handwriting. Okay, let's see. I had one video which I wanted to show you. Let's see if this is the video. Okay, so now the architecture for our machine looks like this. You generate the latent space, you pass this latent space as an input to the machine, and then you generate the output. This process of creating or transforming the images from the real space to the latent space is something which is done by an encoder. So this is the first time in this bootcamp that we are studying about encoder, but this is at the heart of the action chunking with transformers architecture. So I wanted to cover this in detail. Okay, so once we have understood the encoder, let's move ahead. Now the next step is we have got this latent space for handwriting styles. Now we want to feed this into the machine and we want to generate the output. So this is the next part of the story. The first part of the story was the encoding. The next part of the story is the decoding. We have to decode back. But first, let us understand what the decoder or the decoding should do. Let's try to understand that. Okay, so in this visualization, first of all, we are assuming that we have already done the encoding into the latent space of 2 dimensions, Z1 and Z2. Z1 represents the slantness and Z2 represents the neatness. Now, what I want the decoder to do is, I want to take every single sample in the latent space, pass it to the decoder, and bring me back the original image. So now you will see the yellow point moving around. If it moves down, you will get a specific handwriting style, which is slanted towards the left. And if it moves to the right, you will get another handwriting style, which is very specific. So the handwriting style changes as the yellow dot moves in the latent space, which is exactly what we want our decoder to do. So the decoder learns a different mapping. It learns a mapping from the latent space to the actual space. So in this example, where we looked at, let's say, mapping Rohan's handwriting to this latent space, now what we are saying is if we are just given this point, can we generate the real handwriting sample of Rohan with as much precision as possible? So first we did the encoding where we captured the latent variables. So these were the buttons in our machine, which we looked at. So now we have only two buttons actually, button 1 and button 2. So the process of creating these buttons itself is done by the encoder. But the next step, which is when you press these buttons and enter the values, you get the handwriting at the end. What's happening over here? How is this part of the process being taken care of? So that is done by the decoder, and we will try to understand what the decoder exactly does. So in the remainder of the lecture, instead of generating handwriting samples, we are going to take another example, which is to generate handwritten digits. So from handwriting samples, now we are moving ahead and we are taking this task of generating handwritten digits. Now, handwritten digits are also very similar to handwriting. The only difference is that you have numbers instead of letters now. So the size of the image, which is 784, that remains the same. And here also you have to first decode the hidden fact, or you have to understand the hidden factors of variation or the secret recipe or the latent variables which govern the variation in the images. So here also we'll be assuming that there are two latent variables Z1 and Z2. Okay, so let's assume that we have chosen a point in the space which is supposed to correspond to the number 5. Now we want to understand if we take it back to the how to take it back to the real space. How do we transform it from the latent space to the real space for this number 5? So let's try to understand this. We want to pass it to the decoder and decode the number 5. So first we need to understand how does the number 5 exactly look like. So we can divide it into a bunch of pixels. Here we have 28 pixels on this side, 28 on this side. So we have totally 784 pixels. And for every pixel, we have different values. So a pixel intensity of 1 means that it is white, and a pixel intensity of 0 means that it is black. So for every pixel, we have values, and every single combination of 784 values corresponds to a specific digit. So letter 5 looks like something like this. You can see here it vaguely looks like a 5. And wherever we have black, you can see the values are 0 and the rest of the places are white. So the values are 1. So to generate a number 5, we want our decoder to predict something like this. So it looks like all we have to do is output a number either 0 or 1 at the appropriate location so that we get the shape 5. Now, this is definitely one approach and this would also work. But in reality, what people do is instead of outputting one number, what they do is they output a distribution. If we just output one number, we'll get a single number 5 every time. But if you have worked with generative models before, you know that if you ask the same prompt, you can get different answers every time, right? So to capture that variation, what we generally do is, let's say we consider this pixel of 0. So you create a probability distribution where the mean is at 0, but you add a small noise to it. Mean is still 0, but you sample from this distribution. So you end up with values like 0 plus some epsilon, which can be between 0 and 1. So there is a small amount of variability which comes in the image generation process. So let's understand how that happens. So let's consider this pixel, for example. Now for this pixel, I am not outputting a single number, but I'm outputting a probability density. which you can see that the density for 0 is the highest and it gradually wears off. So I'm most likely to pick this 0 value, but sometimes I might pick 0.1 also. So you will get different variations of the number 5 with this approach. Similarly, with this pixel which is white, the mean still lies far across to the right, which is the mean value of 1, which corresponds to a white pixel. But sometimes you might sample, let's say, zero point 0.9 with a less probability, but you will sample it sometimes. And with this technique, what happens is that for every uh, combination of Z1 and Z2, we are not outputting only 784 values, but rather we are outputting. Can anyone tell me how many values we are creating as an output? So let's say there are two values as an input, which is going to the decoder. How many values are coming in as an output of this decoder? 28 into 28. Okay, if we have a deterministic output, that makes sense. But if we are outputting a probability, so what happens is that for every pixel, yeah, that's correct, 28 into 28 into 2. The reason that happens is that for every pixel, now we are not just outputting the mean, but we are outputting the variance also. So we have two values as the output. We will look at a very practical example for this, so it will make sense. So you have 784 into two values. This is not the default practice. Sometimes you have 784 values also, but this also might happen if you take a probabilistic route to the output. So we will look at a visualization for this so that you understand what we covered theoretically. Okay, so the input is this image. We first encode it and we transform it into the latent space. The encoder compresses this data. That's fine. We have already looked at this. Now we take out a point in the latent space and we pass it to the decoder and we generate not just a mean image, which is the mean values for all the 784 pixels, but we predict the probability distribution for all the pixels. And this distribution can be predicted if we have two values, the mean and the variance also. So finally, at the end of it, when you generate multiple outputs, when you sample from this distribution, you will get variety of samples for the same digit 5. So this is what we want our decoder to do. So now, okay, now we will look at the next part, which is exactly how this encoding and decoding happens. And we'll take a practical example of that as well. But we have covered one part of the story here, which is explaining the decoder. And we have looked at what the decoder is supposed to do. But if you paid a close attention, you will understand that I've quickly glanced through the encoder. I have not really explained to you what exactly happens in this encoding process. And if we only had an encoder and a decoder, then shouldn't this lecture be titled autoencoder? Why is it called as variational autoencoder? Can you guys just type in the chat your thought process for this? I will go to that question again in some time, but we really want to understand the variational part in the variational autoencoder in this lecture. Okay, so now we need to understand how does this encoder actually work. Remember what the encoder is doing is that the encoder is taking an input image and the encoder is telling us which area of the latent space corresponds to that input image. So if we take, let's say, Rohan's handwriting, for example, which area of the latent space corresponds to Rohan's handwriting. And our final machine looks as follows. Initially, we just had this part, which is the encoder. So what the encoder does is, the encoder takes the input image, it finds out the areas of the latent space, which is the secret recipe, which is then passed to the decoder, and you try to reconstruct the original image. So this initial machine which does that is called as the encoder. Okay, now our understanding so far is that we take an input image X, we pass it through an encoder, we get a latent representation Z, we pass it through a decoder, and we get the input image back. Now, how is this transformation done from the input image to the latent space? Remember, initially I had told you that every single sample corresponds to one point in the latent space. That was not technically correct. What the encoder does is, it gives a distribution. It does not just give a point, but it tells us that your image most likely corresponds to this latent space, or it most likely corresponds to this part of the latent space. So it gives you a region in the latent space. And this is why the word variation in variational autoencoder comes from. If you just take a plain autoencoder, the encoder step will just give you one single point which corresponds to the image. But in the variational autoencoder, we don't get a point in the latent space, but rather we get a distribution in the latent space where the image is most likely to belong. Now, some of you might be wondering, why do we even need this distribution in the first place? Why can't we just map images to points and then be done with it? So there is a very nice explanation for this, which I want to explain using this visualization. So please pay a close attention to this. I will not explain this as it goes along, but I'll ask you a question at the end. Okay. Can anyone help me understand that why we need the variational part in the variational autoencoder? Why can't we just predict one single point in the latent space corresponding to an image? Why do we need to predict a distribution? Preetham says to reduce the overall search space, memory and compute is saved. Sriharsha says that otherwise we get points in the latent space. Then if we sample something, it will be noise. Anyone else wants to answer this question? Shreyas, come up with new outputs that exact inputs add some variety. Okay, so the answer given by Sri Harsha is actually correct. What happens is even Pramod's answer is kind of uh, in the right track. What happens is that if you, let's say this is your latent space, the example which is given in this animation is, let's say this is the latent space Z1 and Z2. Okay. And this is a point which corresponds to cat. And this is a point which corresponds to dog. And let's say you pick something in the middle here or here. Because your points have a specific meaning, the region nearby the point don't mean anything. So now if you pass this input to the decoder, it's most likely to produce garbage, which makes your algorithm very brittle. And it's it will become robust only when every single area in this region will mean something. So now instead of a single point meaning cat, you can say that the probability for cat is in this region. The probability for dog is in this region. So you fill up spaces in your latent space so that every single point in your space typically means something. This is very similar to what we do in vector embeddings, which are passed as the input to the transformer architecture, where the embeddings which are close to each other in the latent space, like the embeddings which are semantically similar, are close to each other in the latent space. So we are thinking in that direction that we want the latent space to have a meaning. We don't want it to be disjoint chunks, which mean something specific. And this has led to a huge, significant boost in the accuracy of predicting distributions. And I think this paper came out in 2013 on VAEs, and it really revolutionized image generation capabilities of AI models. And after that, of course, we have seen a lot of innovations, but this is something which started it all. So to put together, we have this encoder which encodes your variations in the in the images in the latent space, which itself is something which is challenging because now you don't have to predict one single point for each image. You have to predict the mean and the variance. So you have to predict 2 points for each image. We will look at that in detail in a practical example. Once you have the encoder, the output of the encoder, which is the secret recipe, the hidden factors of variation, the slantness and the neatness of the handwriting, which we are looking at, that is passed as an input to the decoder, which then constructs the final image. And you can't expect this image to maybe completely match this because finally we are compressing a lot of image, we are compressing a lot of data. So we are bound to lose some information. But then we want to maximize this reconstruction. And this actually brings us to the next logical segment, which is how do we train this variational autoencoder? What would be our training objective? Can anyone think what is the loss that we will construct out of these variational autoencoders? So you have an input image and your variational autoencoder predicts something. Yeah, so both Paresh and Sriharsha are correct. You try to match the input image with the output image. And in fact, that is something which is very intuitive to all of us, but that is only 50% correct, as we'll understand. But the rest of the 50% is not very intuitive. It was not intuitive to me, but I've tried to understand it more deeply once I looked at the literature. And it is something which we will look at in detail, but 50% of your answer is completely correct. So the formal representation of variational autoencoder looks something like this. The decoder distribution is denoted as P phi, and the encoder distribution is denoted as Q theta. And the decoder distribution is denoted as P phi of x given z, which means that given the latent variable, we want to predict the output. And the encoder distribution is given as Q theta of z given x. It is reverse because given the input, we are trying to predict the latent variable. We will use this notation briefly in today's lecture when we come up with the training objective. But I want you to be familiar with these terminologies, which you might see in several papers. If you read the original VAE paper, you might see some of these notations there. And I think now you'll start to understand why the VAE diagram always looks like this. The reason this length is larger than this length is because we are compressing the data from a higher dimension to a smaller dimension, and then we are bringing it back. So this is reverse. So the flow is like we encode the data and then we decode the data. And in fact, this structure is very similar to just a plain autoencoder also, but now we know where the variational part in variational autoencoder comes from. Now, immediately we see that there are two neural networks that we want to train simultaneously. And the loss which all of you are suggesting is only related to the output from the decoder. So are you suggesting that the encoder is not included in the loss at all? Let's try to understand what is the objective function. Okay, so people, when they think of objective function for deep generative models, as I mentioned before, you can't simply subtract p phi minus p data because the reason is that p data is not available to you. So what people do is that if p phi is the network that I want to predict and p data is the original images, the original distribution for images x data, people write the objective function as this. We want to maximize p phi of x data. What does this mean? This means that if I take these input samples and put it in my probability distribution, I should get a very high value for this. So I'll try to maximize this. Another way of writing is that we maximize the log of this. Now, we want to maximize the probability that the images which you have sampled from your true data are also sampled from your predicted, can also be sampled from your predicted distribution. So this we want to maximize. Now the problem is that this expression itself is intractable. The reason it is intractable is to maximize this, you need to maximize an integral which looks like this. I don't expect all of you to follow this, but I just want you to get the gist of it. So you need to maximize this integral, which means that finding the probability of x data given z and probability of z. So this has to be done for all the latent variables. which is very hard to find, and this is intractable. So what people do is that they come up with something which is mathematically tractable. So people say that, okay, fine, if you can't find this, find a term, let's call it epsilon, which is always less than the true term, and you maximize this term. So if you maximize E, then true term will also be maximized because it's always going to be greater than E. So this term which we find out, it's called as ELBO, which is also known as evidence lower bound. Now let's look at a simple initial understanding video. But before we do that, I want to explain to you how the ELBO term looks like. So whenever you hear ELBO, you immediately know that it's a framework which is related to deep generative modeling and also in particular variational autoencoders. So the ELBO objective is given by two terms. Term 1 and term 2. Term 1 is something which is called as the reconstruction loss. This is very similar to what all of you were saying, that you want the final output to be as close as possible to the input. This is captured here. But as I said before, this is only 50% of the ELBO objective. Now, term 2 is where it gets very interesting. So imagine that you have the latent space distribution, which looks like this, like very, very random. So what term 2 says is that you want to make sure that the latent space distribution looks as uniform as possible. So you want the latent space distribution to go like this. This is my ideal latent space distribution, which is like a uniform Gaussian. So if your distribution is like this, it will force your distribution in the latent space to come to this point. And this is something which I was mentioning, it's not immediately intuitive, but what we are trying to do in this second term is that, let's say you have distribution of these images, right? Handwriting samples. Let's take that example. Now here you see these samples are distributed somehow randomly. Some of them are distributed to the left, some of them are distributed to the right. Now what we are saying is that we want to train the variational autoencoder such that everything can be captured within a normal distribution with a mean of 0 and a variance of 1. So this is a mean of 0 and everything lies within this circle, which is actually true in this case. It almost does lie in a uniform Gaussian. And why are we so fixated on Gaussian? If you look at the neatness, for example, on average, there are going to be people who are very neat. There are going to be people who are very messy. But the maximum people you are going to get are going to be somewhere in the center, which are average. And this is what the Gaussian distribution signifies. Gaussian distribution tells us that maximum people lie in the average category. There are some which are over performers and there are some which are poor performers, but those are very few in number. So this is the Gaussian distribution and that's what it signifies. So we want to pull the latent space to a Gaussian because we understand that every single phenomena of data distribution, let's say images, handwriting, everything inherently has to follow a Gaussian distribution if you have collected a lot of samples. And this appears like a strict consideration, but it does work in practice. So if you closely look at the ELBO terms, both the terms, the first term, as I mentioned, it's the reconstruction loss, and the second term is called as the regularization loss. And both these terms are combined together to form the ELBO objective using which the variational autoencoder is trained. Now, this is not there in the normal autoencoder, this regularization loss, but it is added in the variational autoencoder. Let's look at a visualization to understand this. This is okay. So let me see if I can find this because I think this will be very useful for all of you to understand. Yeah, I hope you can see my screen. Okay, so the objective that we start off with here is that imagine we want to teleport a cat from Earth to Mars. So this is the Earth cat and this is the Mars cat, okay? And we want to send the cat from Earth to Mars, but you cannot send every single atom. It is too much data. So we create a latent recipe, which is also called as the secret recipe or the latent code for this, which is denoted as Z. And then we send that latent code to Mars and then we decode it. That is our problem statement. Now, in probability, we want to maximize the likelihood, which I was mentioning before. It is denoted by log of p of x. But this is very hard to calculate. It is almost intractable because it considers an infinite integral. So people usually find a term which is called as ELBO or the evidence lower bound, which always lies below this true term, which is the true evidence term. So instead of maximizing the true evidence, what we do is we push the ELBO up and maximize the ELBO so that in practice the true evidence will also be maximized because it is anyways greater than the ELBO. Now we decompose the ELBO into two terms. The first term is the reconstruction term, which is denoted as log of p of x given z. So we are basically asking, does the Mars cat look similar to the Earth cat or not? That is the reconstruction error. All of us understand this intuitively. The second term which we need to focus on is the regularization term, which means that is the recipe written in a standard or a normal or a Gaussian distribution. So if the standard prior is P of Z over here, yellow, and initially we are somewhere in the blue. So we slowly shift it so that it becomes close to the yellow curve. And now you see the usefulness of this scale divergence, and the reason I explained it in the first half of today's lecture is because it forms the expression for our regularization term. The first term here is the encoder, and the second term is P of Z, which is oftentimes a Gaussian distribution. So we are forcing the encoder distribution to be as close as possible to the normal Gaussian distribution, which is what is denoted by the scale divergence term. Okay, so this term is called evidence lower bound, and the KL divergence term is this term which I was talking about. It's term 2 in that expression. I will be sharing my notes after this lecture, so you have some time to go through this, understand these concepts again, and we can again discuss this in the next lecture to make it clear. But this is exactly how the action chunking with transformers is trained on the outset. It also has a reconstruction term and it also has a regularization term. So we need to understand both of these properly. Now what we will do is in the last part of today's lecture, we will take a practical example to understand how a ELBO is actually trained, how the ELBO method is used to train the variational autoencoder. And in this practical example, our concepts with respect to the encoder, with respect to the decoder, and with respect to the entire training pipeline will become clear. Before we go to the practical example, does anyone have any doubts which they want to share or ask in the chat, or you can even unmute yourself and ask the doubts? Okay,
Hi,
I think
Doctor.
yeah,
Thank
Preetham, go ahead.
Yeah. So like I mentioned last time also, like, so I come from the engineering background, so I understand very high level of, the concepts that you're teaching. But
Yeah,
in real life, like building applications, applied robotics applications, right? How much of this do someone like me need to understand to the depth?
yeah, yeah.
Just trying to understand that.
Yeah, so when you're actually implementing the policies in in real robotics applications, uh, there are three, four policies which are extremely important. And out of those policies, one of them is ACT, which is action chunking with transformers. And if you just look at the ACT code, uh, there is a way of directly implementing that in the robot without understanding anything. But then if you want to do further projects, if you want to modify the ACT architecture and improve upon it, improve upon the performance, then unless you know the theory, there is you'll find it very hard to know where to start. So there is an option of skipping some of these things and directly going to the practical, but that will not give you enough confidence to implement these AI policies into real world robots. So in my experience, it gives you a lot of internal confidence when you know how the policies are being trained, and it helps you to design much better policies that actually work. So you need to have sufficient theoretical experience. So even in this course, I'm not going through the derivations, I'm not explaining, but I'm keeping it very high level, very deliberately, so that you are able to understand the individual terms. And whenever you see that in a paper, let's say you read the action chunking paper. Now, in that paper, you will see all these terms used very casually. They don't explain it, but then you'll find it much easier now to read all these papers afterwards.
Understood. Yeah, that makes sense. So, any concepts that you have mentioned to the depth in the class, in
Yeah,
this cohort, right, should be enough to make a
yeah,
few
yeah, yeah. Yes. Now, for
experiments.
example, in the next lecture, we are going to learn about transformer architecture, and I believe it is extremely important to learn because every single, so even ACT, if you look at VLAs, vision language action models, there are so many tiny variations people do, but they don't change the main architecture. So 80% of the work has already been done. But people do small tweaks here and there in the action head. And once you understand those concepts very clearly, then it will help you to get a strong hold of the subject.
Understood. Thank
Yep.
you.
Thanks. Yeah, Pramod's question is interesting. How do we get P of Z? So P of Z is something which is fixed. This is fixed to be a normal Gaussian distribution in most of the practical use cases. Now let's go to the second Sriharsa's question. How is the reconstructor error actually computed, like given the input and output image? Oh, so the minus sign is because the elbow is something which you want to maximize, right? And which means that you want to maximize this term and you want to minimize this term because you need to minimize the KL divergence. So if you had a plus sign, it would mean that you want to maximize the KL divergence, which you don't want to do. You want to minimize the KL divergence between these two distributions. That's why you have a minus sign. And with respect to your first question about how is the reconstructor error actually computed? So that is a very interesting question actually. And we are going to look at a practical example now so that you understand how it is calculated in practice. So I think a lot of all your concepts which we have accumulated in this last hour or so, it will get reinforced as we go through the practical example. So pay a very close attention to this, because this is something which will help you understand these concepts which I have theoretically explained in a much better way. Okay, so what we will be doing is we will be looking at these handwritten digits, uh, which are the MNIST handwritten digits. And these handwritten digits have some underlying distribution, which is P data of X. And we don't know this distribution. So our task is to find P phi of X, which is the predicted distribution, and we want to match it as close as possible to the true data distribution, which is the whole objective that we started out with in this lecture. Now you can see from this that all of these letters, they are following a specific shape, right? So you would probably think that, okay, so this is one has some slant, it is written in a specific way. But calculating the hidden factors, underlying factors of variation, it's very difficult for us to do, because we don't know what factors are causing these variations, right? What factors are causing this 1 and 0 to differ exactly? We cannot pinpoint it. It's a very hard task to do. And this is exactly what our encoder is supposed to do, right? So what we do is we first of all, the objective, or to solve this objective, we use a variational autoencoder. That is our first step. And this consists of an encoder and a decoder as well. Now, the way the encoder is set up, let's try to look at the encoder first in detail. The encoder objective of the encoder is to take any image. Let's say I take the image 1, pass it through some neural network, and predict the latent representation for this, which is Z1 and Z2. So I want to predict where does this point lie in Z1 and Z2 space. Not just that, the word variational autoencoder comes because we are not predicting Z1 and Z2, but we are predicting the distribution around this. Now, how do we transform this image to something like this? First, let us unpack how many dimensions we have. So here we have 28 dimensions over here and 28 dimensions over here. So overall, we have 784 dimensions. And if we are transforming this to just Z1 and Z2, we will have only 2 dimensions as the output. But now here, since we want a distribution, for Z1 we have a mu and a variance, and for Z2 we have a mu and a mean and a variance. So in reality, we have 2 values for the mean, and we have 2 values for the variance. So the input of our neural network is 784 dimensions, and the output of our neural network is 4 dimensions. Let's try to see how this looks like. Yeah, so this is how our encoder architecture looks like. We take the input image, we pass it to the encoder, and we generate 2 mean values and 2 standard deviation values. Now, in practice, we use an architecture like this. We use one hidden layer with 400 nodes. So from 784, we transform it to 400, and then we predict these two as the output. So the mean and the variance. Now, how do we predict Z from the mean and the variance? You simply do mu plus sigma times E, where is just a random variable which takes a value between 0 and 1. So this is the encoder architecture that we have used in our code. Okay, so now as the first step, what we have done is we have taken an image and we have transformed that image into a latent representation, which looks something like this. Something like this. Okay, now what we want is in the next step, we want to pass this to our decoder and we want to generate this image back. So the decoder is exactly reverse. It takes the value of Z1 and Z2, which are two values, and it predicts the 784 mean pixel values as the output. Here we are just predicting the mean, we are not predicting the variation at all. So we have 784. So it goes from 2 to 784 in the decoder. So we are going from the latent space to the actual space. And the decoder distribution looks something like this. We take the two values from which are coming in from the encoder, we again pass it through the hidden layer, and then we project it to the output, which is again 784 dimensions. So we go from 2 to 784. So you can now imagine the entire architecture. I think, yeah. First we encode it to the latent representation and then we decode it back. This is the overall architecture that exists in a variational autoencoder. Now, this encoder and decoder might take different architectures in different papers. For example, in action chunking with transformers, people use a transformer encoder here. And they use a transformer decoder. Here we have simply used a neural network, but people use different architectures to represent the encoder and the decoder, but the objective, broadly speaking, stays the same. So this should be one takeaway from this lecture, is the encoder's objective is to convert the real data into a latent representation, and the decoder's objective is to convert it back to the real space. Okay, so this is the overall encoder-decoder architecture, and now let's understand how the ELBO loss is defined. The way the ELBO loss is defined is we have the reconstruction loss as the first. Now, how is the reconstruction loss exactly calculated? The goal of the reconstruction loss is to make the output image look exactly the same as the input image. So we compare every pixel of the input with the output. If the original pixel is black and the autoencoder predicts white, the penalty is huge. If the VAE predicts correctly, the penalty is low. So we just use a simple binary cross entropy loss here. I don't expect you to understand this, but this is something you can read up after this lecture to understand what this loss is. But the main idea of this loss is we are basically making sure that our prediction image looks as close as possible to the original image. So this is fairly simple to understand, and then we predict the KL divergence loss, which is we force our distribution to become as normal as possible. Okay, so I have given more details about this KL loss in these notes, but before we explain the output, I want to share this notebook with all of you so that you can connect and you can actually try it out. This gives a lot of confidence when you actually run something in practice and you see it working. You get a lot of confidence about the individual concepts and overall you start to understand things in a much better way. So first let's connect this. I think it took some time for me to train, but let me walk you through the individual sections. The first section is where you install the different libraries. So we have mostly the torch package, we have matplotlib, numpy. Then we load the MNIST dataset. We use 60,000 images for training and 10,000 images for testing. Next, we define the VAE model. This is exactly same as the architecture which I showed you. First, we have the encoder and then we have the decoder. This is very similar. You will be able to understand this now. Next, we define the ELBO loss. You can see the reconstruction loss is the cross entropy loss, and the KL divergence is given by this formula. I have given the intuition for this formula in the notes. You can go through it. And then we can construct the final ELBO loss as an addition of the reconstruction loss and the KL divergence loss. Here we have considered only two latent dimensions, as I have been talking about throughout this lecture, but in reality you can have a lot more dimensions. For example, in the action chunking with transformers paper, they are using a total of 512 dimensions instead of two dimensions. But this helps us to understand the concepts in a much better way. Then you have the training and the testing loop, and you train the VAE. This takes some time to train. Otherwise, I would have trained it right now. I have trained it for 7 epochs. And you can see the loss and the reconstruction KL loss going down. Now, the first thing that we want to visualize is, remember we had said that we are forcing the latent space to become Gaussian. So let's look at if that is actually happening. So here is the GIF I created from this distribution from the training. So you can see the latent space slowly evolves with time. It doesn't really become a Gaussian, but it is kind of centered around the center. You can see it's like almost in this area. So it's trying to orient itself towards the middle, but more often than not, this is not very feasible. So you try to get latent spaces which have a final distribution of something like this. So here you can see that this is the latent space distribution. And remember, we are only using two dimensions here. So this is the digit 0, which is shown in blue, which is encoded in this region of the latent space. This is digit 1, which is encoded in this region of the latent space. This is digit 2. So similarly, you can see there are different areas in the latent space where we have successfully managed to encode these digits. Okay, so yeah, so let's look at Pramod's question. Yeah, Pramod is saying that the reconstruction loss has the notation or the variable z inside. So how can we understand? So, okay, so in the reconstruction loss, we are trying to maximize this. Which is, given the latent variable, you try to maximize that the sample which you have generated is from the original distribution, or it matches the original image as close as possible. But how will you find this? How will you basically say with confidence that the probability of sampling of that original image from your distribution is high? So you essentially, what you say is, okay, this is what I need, and I have access to my generated image. I have access to my original image. So what I will simply do is I will look at these pixels one by one and see how these pixels are close or different from each other. If my generated pixel is very close, I will be confident that uh, this image or this image is more likely to be sampled from my distribution. So it's like another way of uh, calculating this. And in fact, there is a way of formally proving also that this is same as doing this, but usually in most of the cases, people simply take a cross entropy loss between the final image and the original image. I can share with you the details of why this is true, but if you write down the equations, you will see that this eventually boils down to the same equation. Okay, so if you look at the latent space, it looks something like this, which was the initial hypothesis that we started out with, that we want to map every single image to a distribution in the latent space, which is what we are getting. And then you can actually you can reconstruct from using the decoder. So these are the type of reconstructions that you get. This is the original image and this is the reconstructed image. So you can see that our variational autoencoder is able to construct the image, but it appears a little bit blurred. So blurred images are one of the key drawbacks of VAEs in practice. But this is something which was really amazing at around 10 years back, because we had a deep generative model which we could sample from and create new images which look something like this. This looks a little bit odd, but anyways, now we have a model which we can sample from. And this was the first goal that we started out with in the deep generative model lectures, that we don't have access to the distribution, to the true distribution. We only have access to the data samples. So we want to create a model which can predict the true distribution so that we can sample from it. And the way we do that is that first we encode the samples and then we decode them. So that becomes our method for generating new samples. So this was one example which all of you should definitely run and experiment with it. Try with more number of epochs. I think you will get distribution which is more closer to the normal distribution. And please try to train this and run this notebook, and then try to come back and understand the definitions and whether you understand all the concepts properly or not. There is also one more thing we have not covered over here, is what if you want to just generate a digit 1? So how do you sample from this conditionally? Or how is that done? So now I'm sampling from this decoder distribution, right? And I'm getting random images depending on whatever Z value I input. So I input one Z value to the decoder and I get an output. So if I keep changing my input, I'll get different outputs. But what if I want to condition the output on the digit 1? Like I just want the images to be number 1. So this is something which is called as conditional variation autoencoder. And I will share a blog with all of you. It is very similar to this. There is one small step which is added uh, in the training process. Usually we pass, along with the images, we also pass uh, the digit, like the specific digit which you want to condition it on. And it's a simple addition to the training data which is done. And then we'll see that only specific images are generated as an output.